So, okay, it seems to be about time to start. So, okay, my name is Florian Hess. I'm from Berlin actually, and so the title of my talk is Aspects of Elliptic Curve Cryptography. What I would like to do during this talk is to kind of attempt the impossible, in a sense, to give you kind of a very brief introduction actually to how the whole thing actually works. But also, what I would like to attempt, say, is to also give a little bit an overview or, say, report on the state of the art actually on the security of the elliptic curve discrete logarithm problem. I do have quite a number of slides, for which I apologize, because that means that I probably have to go quite fast, and maybe as we go along I might have to skip a slide or two or so. Okay, so this is the overview. Just as a short introduction, reminder of basic cryptographic tasks. Then I would like to move on to, well, explain how finite fields work, how algorithm encryption works. This is just more like a tutorial, say. Then we move on to group-based cryptography, elliptic curves in particular, and finally, security aspects and attacks. Okay, so, well, the first few slides will be very easy, so anyway, hopefully it's not going to be too boring. There are some funny pictures to make it a bit more lively, because otherwise the whole subject is quite technical and mathematical, and there won't be any pictures later on. Okay, so here we have Bob, and Bob, well, that is one guy. He is Alice, his secretary, say, or whatever, and so both, Bob actually wants to send Alice a message. Okay, of course, the whole message, well, the aim is that nobody else actually can read the message. So if there's Oscar, somebody who can actually intercept the message, say because it's a wireless LAN connection or whatever, well, it would be quite easy actually to read all these messages. And this is one assumption in cryptography actually, that when parties actually exchange messages, that there may be intercepting parties who actually can read all the transmissions, and the goal is that nobody else can, well, that these intercepting people actually cannot deduce any information from the information they see. Okay, so here we go. So the whole, the letter, if you open it up, say, there should be some funny signs, some funny letters inside, which do not make any sense to the intercepting guy there. So this is what encryption is all about. So there's basically two fundamental ways to proceed. So one could be to use two secret keys, which are the same for Alice and Bob, which they actually could agree on prior to communication. Well, and this secret key could somehow describe, say, a secret method or something by which to encrypt and then also to decrypt the message which is transmitted. But this is not the way we would like to proceed. So this is not, well, the way elliptic curves actually will come into play. Elliptic curves come into play into this setting here. So the blue things are now is public information. So the blue things are public keys, and the red thing is a secret key of Alice. Okay, and what we would like to do is the following. So Bob actually uses the public key, yeah, to encrypt the message, which is then transmitted. And finally, when Alice receives it, she actually can decrypt the message using the secret key. Yeah. Okay, so the public key is public, the secret key is secret, and Bob, who intercepts, well, Oscar, who intercepts the message, well, he doesn't know the secret key, he only knows the public key. Yeah? And the aim of the whole thing is that using the public key, you can't unlock the message, you can only unlock it when you have the secret key. That's basically the paradigm of public key cryptography. Okay. So, well, that's the first fundamental task. There's also the second one. So the first is encryption with a public key and decryption with a secret key. That's public key cryptography. And there's also kind of a dual operation, which might even be more important. Well, that depends on the applications, I guess. That is signing with a secret key. So you sign with a secret key, and the signature, the digital signature, is verified using the public key. Yeah? Well, the idea being that, okay, you can verify. So everybody, because everybody knows the public key, can verify signatures, but only the person in possession of the secret key can actually sign it. Yeah. Okay, so this operation requires some sort of one-way function, which means like, well, you have some data, and you can kind of easily transform it into some other data, but the way back actually, so which would be decryption, say, should be hard So inverting this function f should be hard. That's what one calls a one-way function, say. Okay. So the interesting thing now is that's more, say, theoretical consideration, but well, it is interesting to know, I guess. Well, from a theory point of view, it's not known whether these functions actually exist. Yeah? So in theory, it could be that all functions are easily invertible if one is only clever enough, or if one is kind of an alien or so, and then the whole public key cryptography would actually completely collapse. Yeah? Well, under current human knowledge, there are quite nice candidate functions actually where one suspects they might be one-way functions, but one just cannot prove it. And those ones are actually used in public key cryptography. Okay, so candidate one-way functions. That's yeah. How do you obtain these things? And that's where mathematics comes into play. So basically all candidate one-way functions are actually obtained by computational mathematical problems. So you have kind of a mathematical problem where you would like to compute a solution to. Yeah? And these problems should be hard. You know, otherwise it would be easy to invert the function. That's the main idea behind the whole thing. And these mathematical problems in particular come from algebraic number theory. Okay, so here are some inverse operations. Well, just some examples, say. So the classical example is factoring integers. That's used in RSA. So it's not really equivalent, but it's, say, related to factoring integers. So if you take two integers, multiply them together, can you actually decompose it into the two prime factors again? Say that's the question which is considered here. Another thing, and this is what we are going to look at in the talk, is discrete logarithms in finite fields and elliptic curves of finite fields. Well, I'll explain that later. Other things which we are not going to look into are shortest and closest vectors in lattices and code words, and also solving multivariate equations, so other mathematical problems, but we won't be concerned with these ones here. Okay, and why elliptic curves? Well, elliptic curves lead to very efficient systems compared to factoring integers and just finite fields. Okay, so this now will be kind of 9th grade or so mathematics. It's probably kind of well, if you haven't seen it before, it might be a bit unused, but in the end, it's very easy. Okay, so integers, integral numbers, yeah? So, well, just a little bit of notation. Well, it's usually denoted by z, say, so it's 0, 1, minus 1, 2, minus 2, 3, and so on. So just integral numbers. Say what you get if you say int in C or something. Yeah? Okay. What can you do with integers? You can add them, subtract them, and multiply them, so basic arithmetic operations. What you can't do is, we first go on to prime numbers. Okay, so prime number, just a quick recall here. Well, that's a non-negative integer which is only divisible by 1 and itself. Huh? Okay. Example. So easy examples are 2, 3, 5, 7, 11, 13. Then there's kind of a gap, which, well, we don't have to list them all. And then there's a more interesting prime, basically a very big one. And those are the primes actually which we will be concerned about in this talk. Everything should be big, eh? Otherwise it's easy. Okay, so every integer can be decomposed into prime numbers. That's probably familiar, I guess. So 350 can be written as 2 times 5 times 5 times 7. Hmm? And okay, we're on with division for the remainder. So in Z, of course, well, addition, subtraction, multiplication is all possible, but division is not possible because, well, if I divide 5 by 3, it's not going to be an integral number. Yeah, there will be some kind of remainder. And okay, so this is division with remainder. Suppose we have two numbers a and p greater than 0, say. Then we can write every number a, well, as h times p plus r, and r is the remainder and h is the integral division. Hmm? Okay, so typical computer notation say a, well, this h there would be a div p and the r would be a mod p. Yeah? So these reminders are always, well, what one gets when one does say a mod p, or in C say a percent sign, yeah, p, then that's what you get. Okay, example 5 div 3. Well, that would be well, 3 only fits in ones into 5, so that would be 1. And the remainder would be 2, because 5 is equal to 1 times 3 plus 2. Another example, which may be a bit more strange, so minus 1 mod 3. Well, since we would like to have the remainder being non-negative, well, we just add 2, and then we get actually, we add 3 and get 2. So 2 times 3 mod 5 would be 1, because that's 6, so minus 5 is 1. Okay. So what one frequently does in cryptography is computing modulo prime numbers modulo. So you do a computation and then you reduce the result modulo the prime number, which means that your results will lie in the set fp, so that integers from 0 up to p minus 1. So p could be really large now, like the prime we saw before. And okay. And the interesting thing now is, well, if you do the normal integer operations and then do the reduction thing, you again get kind of an addition, subtraction, and multiplication, like in Z. Yeah? It's completely analogous. It's just like, well, a bit twisted, say. But interestingly, if P is a prime number, you can always invert and divide elements in the set Fp. So for example, if in F5, so P is equal to 5, if I have 2, then, well, if I multiply 2 by 3, I get 6, but 6 mod 5 is 1. So in some sense, 2 times 3 is equal to 1 in this set, if you define kind of a funny multiplication, for example. So if I work, for example, in R, the field of real numbers, well, every element is invertible, so every element has an inverse, such that element times inverse is equal to 1. Yeah? And what happens is in these, in this funny FP, the same is true. Yeah? Every element can be multiplied by another element, by a more suitable another element, such that we would get 1. Yeah? That's the thing. So, okay. Just a side remark, these inverses and divisions can actually easily computed using the Euclidean algorithm. Okay, so this leads us to finite fields. So the following P is always a prime number, and Q, is always a prime power with R greater or equal to 1. Okay, so this set Fp of P numbers, which we saw before, with multiplication and reduction mod the prime, with these arithmetic operations of adding, subtracting, multiplying, and dividing. The whole thing with these 4 operations is called a prime finite field. Yeah? That's just a terminology, a mathematical terminology. And these things are really the basic building blocks which are very frequently used in cryptography. Okay, so these are the most easiest ones. There's also more difficult ones, which I don't want to explain in great detail. So if you replace the P by the Q, which we had before, the prime power, then you can also make a finite field of Q elements, where every element can be added, every 2 elements can be added, subtracted, divided, whatsoever, multiplied. And this FQ is actually obtained in quite a kind of a similar way. One actually uses polynomials, like one knows from school. So polynomials where the coefficients are from Fp, and the polynomial has R coefficients. And then one does the very same thing like before. One does polynomial multiplication, polynomial division with remainder, known from school, I hope. And if you do all the same, then the set Fq actually becomes a field again. Yeah? So this is the general form of finite field. Okay. So if this was kind of too fast maybe, or you haven't seen it before, if you're uncomfortable with it, another easy way to figure out what's actually going on. So this was more like the explanation of the internal workings of the thing. You can also think of that somebody actually writes, gives you kind of a C++ library or something, and there's a class for objects and instantiation of these objects. You have the following operations like plus, minus, multiplication, division, equality test, whatsoever. Well, you don't have to know actually what's happening inside the elements. You just know that you can apply these operations like you are used from say, field of rational numbers or something, or from R. Yeah? It's the very same thing. So the whole thing can actually be implemented, and it works very nice in practice. Okay. So now we come to the main thing, discrete logarithms. This is a bit complicated to say, not really. So we also, another prime enters the scene, so this is called L. And there's a requirement that L actually divides the number of finite field elements except, where we exclude 0. Yeah? We don't want to work with 0, we only work with the other ones. And this number, which is q minus 1, should be divisible by this L. Okay. So here's the statement. There's a particular element in this finite field, which, if I raise it to the nth power, gets 1, and which has the following property. So every other element with this, if I raise it to the power of L equals 1, every such element y can be written as a power of this original element g in a unique way. Yeah? So this x is actually uniquely determined in the interval specified there between 0 and L minus 1. So this is just the statement. Well, the proof is a bit complicated, but I don't have to, well, it's not of concern for us here. Okay, so this x, yeah, which is, well, this exponent x is called the discrete logarithm of y in base g. Yeah? So this is really like what is used from normal logarithms. The exponents are always the logarithms to the thing which is, well, is underneath the exponent. And it's called discrete because x does not vary over the real numbers, but there's only finitely many possibilities, namely L possibilities in this case. So that's why it's called discrete. Okay, so a quick example. Well, 3 to the power of 4 is equal to 4 mod 7. Well, that's easily computed. Well, for example, 3 times 3 is 9, mod 7 is 2, and 2 squared again is equal to 4. That's one way of computing. And here's a more typical cryptographic well, operation. Say, take a big number, take another big number, well, compute the whole thing, mod the prime number, which we saw before, and then you actually get something out. Okay, and the thing in the exponent then would be just the discrete logarithm. And those are, well, these long integer calculations are the ones which we are actually using, well, in practice, say. Okay, so if you are given g and y, finding these x's, yeah, which exist, but, well, computing them, like having them as a real number, yeah, this problem is called discrete logarithm problem. And this is one of the basic building blocks which are used in cryptography. So, kind of very important algorithmic problem. Okay. So, well, here are some typical values. So the prime power, well, or the prime q should have more than 300 decimal digits, say, and this L more than 50 decimal digits. Those would be typical values which would be taken into consideration, say. Then, computing g to the power of x from g and x is easy statement. No? That's computer does it in no time. Well, almost no time. But the inverse operation, like finding x again, if you're only given g and this power g of x, yeah, as an element, say y. So finding this x, finding this discrete logarithm, this is a very hard problem, and the computers would take forever if q and l are just big enough. Yeah. Okay, which means that this exponentiation is a candidate one-way function, which I mentioned before. Yeah? So easy to compute images, very hard to invert. And the discrete logarithm problem itself is just, well, is the same as inverting this exponentiation function. Okay, so here's a quick example how this actually would be used. Well, this is more like an idealized example. This is encryption, so we have Bob and Alice again. So key generation, public key, private key. So the secret key, Alice would choose the secret key just as a random number x in this interval. And the public key would just be y, g to the power of x. So the red things are secret and the blue things are public. Okay, because the blue things are public and because it's complicated to compute x, x is kind of well protected still. It remains secret, that's the assumption. Okay, so this y is sent to Bob, so he can actually use it for encryption. He wants to encrypt messages, so messages themselves, technical things, say, would be represented as elements in this finite field fq, but not include, well, we exclude 0 in all computations. Okay, what would he do? Encryption by Bob. Well, what he does is he chooses a random secret number r between 0 and l minus 1, and then does the following computation. He computes g to the power of r, that's one computation, and then he computes m times y to the power of r. Yeah, it's just the easy computation, say. Okay, what he then does is the data he has computed, he sends this to Alice. So these, and the data just looks at two elements, UV, say. Yeah? What is Alice doing? Okay, Alice computes just this element, V times U to the power of minus X. So, and the claim is that this would actually be M again. And here's a little computation, say it's kind of easy if you plug in the definitions. So V times U to the power of minus X is, if you plug in the values here, the right values on the right-hand side, well, then you get what's written down there. I don't want to read it. And the whole thing actually cancels out the G thing, and M is the only thing which remains. Yeah? Okay, so if Bob does this, then actually Alice gets the message M. So why would it be secure? Well, if you look at the g to the power of r and m times y to the power of r, well, m is the message, but y to the power of r is just a random element in the finite field. So if you multiply both together, it's also just a random element of the field in some sense. Yeah? So roughly speaking, M is already completely disguised, and the relation between y to the power of r and g to the power of r is hard to compute. Well, that's kind of related again to the discrete logarithm problem. So it's a little bit tricky to think about, and but I don't want to spend too much time on it because we want to move on to elliptic curves. So this is just like how one of these basic cryptographic primitives would actually, in principle, work. Okay. So abstraction. So this was, say, easy, yeah, so far. So just some modulo computations. Maybe these FQ things are a little bit strange, but if you stick to FP, it's really kind of, well, you could explain it to pupils in the 9th grade, I would assume, if you had enough time or so. Anyway, okay, but now comes a little bit more, well, now comes in what mathematics normally does is, well, you have some operation and then you actually wonder, are there, well, what are the basic ingredients? Yeah, what is the main essence of the whole thing? Huh? Okay, so we ask ourselves, what have we used so far? Okay, so we have computed in these funny finite fields, but we have only used multiplication and inversion. We haven't used addition and subtraction whatsoever, yeah? Which are, well, these operations are in FQ, but we haven't used them. We also haven't used the zero element. So this is actually useless for us, yeah? Okay. And this is one of the ways actually one could proceed, okay? And then just, well, let's fix the operations which actually need. So in some sense, we make a definition of a virtual class and say what virtual methods we actually require for somebody to implement. Yeah? So, and this gives, well, okay, let's say a set G where elements can be multiplied inverted in a sensible way. I don't want to specify this. So it's mathematically called a group, just a name. Yeah? It could be a class name, say. Okay. And well, what comes out if one analyzes, for example, Al-Gamal encryption, that it in principle works in every group where elements can be represented in the form of g to the power of x. So those groups where this can be done are called cyclic groups. So it's a kind of a special type of groups. Yeah. Okay, and the conclusion now is, okay, here's first the question, but the conclusion up to now is, okay, if you have such a group with multiplication, inversion, and which is cyclic, so every element can be written in the power of g to the, as a power of g to the power of x, then we can do encryption, say. Okay, natural question, are there further well-suited groups except the ones we have already been considering? So the ones, well, we have been considering are those multiplicative groups of finite fields, where we include the zero element. Huh? So here's the answer. You might have guessed it. Of course, elliptic curves. Yeah? And all right. And the point is also that, as it turns out, and this, well, I mentioned it before, they actually seem to be better suited than finite fields. Okay. So now we come to the main thing. Well, what is an elliptic curve? It's not so complicated, but well, the formula in the end it adds up. So. Anyway, so we have again the Q, which is the prime power, and let's suppose for the moment that P is greater or equal to 5. Technical condition is not so important. Okay, so now we take two elements of the finite fields, which also have to satisfy some conditions which are not really important. Okay, so an elliptic curve itself is just an equation. It's nothing more. Yeah? It's an equation, y squared equals x cubed plus ax plus b. That's all it is. There's nothing more behind it. So what one usually considers then, points on the elliptic curve. Yeah? So what are these points? Okay, that's written as E of FQ, just a notation, and it's the set. So it's the set of all tuples, x coordinate, y coordinate in FQ. Yeah? So now we are not only considering one element of FQ, but we're actually considering pairs of elements of FQ, which have the following relation. So if I take the second coordinate, well, if I square it, then this should be equal to the first coordinate cubed plus a times the first coordinate plus b. So I take all these tuples. Yeah? The finite field is just a finite set, and so it's clear that this would also be just a finite set, like well, if you do a mental game, say. Okay, so we take all these points, and then there's one particular point which you also have to include, which is symbolically written as O, or 0 if you wish. Side remark, slightly different equation for p equal to 2 and 3, but that's only technicalities. Huh? Okay, so, and the funny thing now is, and this is what actually mathematics had provided long before cryptography came into play, so this the theory of elliptic curves, not over finite fields, say, but over other fields, it's actually dates back to the 19th century. And that's also, well, the following also has been discovered in the 19th century. So the point is, if you take 2 points on an elliptic curve, there's a way to multiply them in a sensible way. And this point O is the neutral element, so if P times O, say, is always P again, so it doesn't do any operation. It operates like 1, like multiplication with 1. Okay, and well, for historic reasons, and in order to confuse you, I guess, multiplication is now written as addition. So whenever I would like to write star, I actually write plus, and whenever I do an exponentiation, this turns into a multiplication by x. So instead of writing p times q, I write p plus q, and instead of writing p to the power of x, I write x times p. So this is the way you normally do it with elliptic curves. It might be a bit confusing, but the logic is the same. It's just notation. Okay, so as it turns out, well, that's what I've said, this E of Q is actually a group. And, okay, let's see. Here's a quick picture. This is, well, this is actually does not apply to our case. So this would be an elliptic curve over R in the plane, the normal plane, and the thick line is the graph of the curve, and the point addition can be visualized. So if I have 2 points P and Q, what you do in order to find the addition point, you make a straight line and you compute the intersection with the curve. There's a third intersection, that's always true, but has to be proved. So this would be R in this case. And then you do a horizontal line and you take the second intersection, and this will be the addition. So this is how it works. And if you write this all down in formula, blah, 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 then in the end you will get formula how to perform elliptic, well, the addition just by using the coordinates and not doing any geometric stuff. Okay, so normally this picture does really not apply to cryptography, because once you have worked out the formula, you're not interested in the picture anymore. I just wanted to show it to you. Okay, same slide as before, which we had. So one additional point. So if this was all too complicated and you have already forgotten all the things, all you have to remember is the following. Like with finite fields, somebody could give you, and this is actually in fact done in most applications these days, so you just download the library and there's a class, say elliptic curve point. You can have instantiation of these objects, and then there are methods to add them, to subtract them, or to multiply them with integers. Well, you can also construct them, say. So basically, you can treat the whole thing as a black box, if you wish. You only have to know, there are points, and there's a 0 point, and if I add the 0 point, nothing happens, and I can do these arithmetic operations. How it works in practice is then actually not so much important anymore. I just wanted to expand a little bit of what's behind it. Okay, so here we moved on to the analogous thing, like for finite fields, discrete logarithms. So now again, this prime L enters the scene, but now we have, the requirement is that L divides the number of elliptic curve points, not the number of finite field elements, except 0, but now we have to divide all the points which we have on the elliptic curve. That's the requirement. And then it's just the same. So if there's a particular point P, such that L times P is O. Before we had G to the power of L is equal to 1. With the following property, every other element with this condition can be written as a multiple of our base point P. Before we had every other point Y can be written as G to the power of X. It's just the same. Okay, and again, this exponent X is now called discrete logarithm, although the whole thing looks a little bit different on the slides. And the problem of finding X given P and Q is the acronym for this is ECDLP, elliptic curve, discrete, and logarithm problem. If you ever see it in the literature, then you know what it is. Cryptography also likes these acronyms, so there's all sorts of them. Okay, hardness of the DLP. So this is the main result, basically, or main statement, or a very important statement, say. It is believed, that's not proof, it's believed that the most efficient method for solving a random ECDLP in an elliptic curve, where the elliptic curve A and B are chosen at random. The most efficient method cannot take advantage of the special structure of E. Maybe some additional clever information which E might provide. So that's the one assumption, and which then actually implies that it requires at least square root of L many steps to compute a discrete logarithm. So this number L to the power of 1/2, this is kind of a runtime estimation which you can have in every cyclic group. So that no matter how the cyclic group is actually defined, if somebody gives you a class, you don't know the definition of the group, you can solve discrete logarithm problems in time, say L to the power of 1/2. Yeah? That can always be done. And the assumption is that for elliptic curves, you cannot do it better by using special information. Yeah? That's, well, under the requirement that the elliptic curve is randomly chosen. Yeah? Okay, so in other words, it's expected, well, I said this already, that this ECDLP has maximal security in group-based cryptography in relation to the group size. Yeah? So, which means like it's kind of an optimal case, say. Yeah? Okay, a little bit of history. Elliptic curves themselves have been proposed for cryptographic use in 1986. Like public key cryptography itself came up in the mid-70s, say. Shortly afterwards, finite fields were proposed for use by Gamal. And then it took a couple of years actually to realize that elliptic curves might also be a very viable alternative. So just in order to compare the running time, so if you have a DLT in the finite field, the runtime is more like the following expression. It's the minimum of L1/2 because that's kind of an upper bound. You can always do it that fast, but you might be able to do it faster, namely like the expression which I've written there, this exponential of some constant times log Q to the power of 1/3. Especially if L is roughly equal to Q, then this second exponential expression is much smaller than L to the power of 1/2, which means that the DLT is not as secure as the elliptic curve DLP. Yeah? Or if you would like to have it of equal security, then you have to have increase Q in comparison to L. Okay, so here are some numbers. So the whole table is kind of assuming equal security of the various underlying crypto systems, say. So there's a block cipher key size in the left column, and some example block cipher, the elliptic curve cryptography key size, which you would have to have. So that's in bits. Yeah. So your Q and your L should have as many bits as stated there. And this is RSA, I didn't go into detail, or FQ star, that'd be kind of easy, similar. This is the number of bits in the queue you would have to have, yeah, in order to achieve, well, every row has the same security level. Okay, so 80 bits would correspond to ECC key size of 160, say, about, and to RSA 124, which is considered a bit small these days. So traditional triple DES is 112 bits, ECC is 233, and RSA just 2048. Kind of, well, that'd be kind of okay. If you want to move on to more modern things, say, well, the three AES instantiations with 128, 92, and 256 bits would require, well, as stated, I don't have to read it. So what's interesting is that the elliptic curve key size does not increase as fast as the RSA and finite field key size. Huh? And this is because of the runtime I showed you on the other hand slide, because elliptic curves kind of, in comparison to the group size, they provide, well, that's what one thinks, they provide optimal security, but with FQ and RSA, that's not the case. It's actually much less than the generic security you would expect. So, which means that in order to achieve the same security, you need to work with much larger group sizes. Well, there's no problem in this, in principle, only that your computations get much slower, of course. Yeah? And if you move on to, say, biggest AES of 256 bits, then ECC with 517 bits is still practical, say, but RSA or finite fields with 15,000 bits is not really practical anymore. Okay, so in principle, why use elliptic curves? Just as an intermediate remark here. Well, it's for efficiency reasons. Yeah? Well, you can have the same security in both systems, say, only that then the efficiency of the ones are, well, of RSA and FQ are much slower than on the elliptic curve side. Yeah? And if you want to have the same efficiency, say, then RSA and FQ would be less secure, or would be expected to be less secure than elliptic curves. Okay. So, problems and questions with respect to security and practicability. Well, when working with elliptic curves, it's not so easy because there are some things which one has to know. So we had this prime L, yeah, and the requirement was that L divides the number of points on the curve. Otherwise, the whole theorem doesn't work, which I stated with the discrete logarithm, it doesn't make sense and the whole thing collapses and wouldn't work at all. So this is an essential requirement. But what is E of Q? What is the number of points on the elliptic curve? Well, you can't just read it off A and B, just, well, there's no simple formula to plug it in. And that's kind of, or has been a big problem in the past. Well, research terms, well, under research terms, it arranges, or well, it's normally referred to as point counting on elliptic curves, the whole thing. Yeah? Count the number of points on an elliptic curve. Okay, so this is one basic question. How do we actually construct elliptic curves such that we have a large prime L of size, say, roughly equal to Q, dividing the number of elliptic curve points? Okay, then the question is, how secure is actually the DLP on the elliptic curves? Yeah? So, well, that's a thing which has to be investigated, of course. And one question is, well, it might be secure in general, say, but are there maybe special cases where it would be easy, and how can one identify these easy cases? Yeah? Another question. And the third question is like, well, when working with these things, well, you implement your elliptic curve as, say, a class, and you have these addition, subtraction thingies as, or multiplication by integers as member functions. Of course, you would like to optimize the whole thing, so it actually consumes as less computing power as possible, so your server can do as many requests as possible, say, or use as less memory as possible if you want to put it on a smart card or something. And well, for example, one thing is, well, in this direction would be point compression. So if you have a point, you can actually compress it to use up less memory, for example. Okay, so in the remaining time, I would like to discuss 1 and 2, especially 2, say, and 3, I don't want to say anything about it anymore. This is more like, say, techniques, and this, well, I just want to leave it aside. Okay, so construction of suitable elliptic curves. So there is sort of a formula for the number of points on elliptic curves, but it's not, well, you can't use it for computation, say. So what one knows is that the number of points is equal to Q plus 1 minus a mysterious number T, but T is unknown, yeah? The only thing which one knows is that in absolute size, T is less than or equal to 2 times the square root of Q. That's the only thing one knows. Well, this is kind of a celebrated theorem which was proved in around 1940 by a German mathematician also. And anyway, at this stage, yeah, so when these things were considered in mathematics, by the way, interestingly, it's there was no cryptographic idea in the background for some reason. So these things actually have been studied for pure theoretic interest, say, and it only turned out, like in '86, as I mentioned, that it was realized that these things actually could have practical use. Okay, so I need to know L divides the number of elliptic curve points, as I pointed out. So the question is how to compute T, say, yeah? Okay. So basically there are 3 methods of proceeding. So one would be just to take random A and B, so say let's take a random elliptic curve, randomly choose A and B, and then compute the number of points. Okay, this is kind of an empty statement. The computation of the number of points, so the computation of this T can be done, yeah? But this is quite of a complicated task and occupied much of the 90s in some case, and there was kind of a, say, recent breakthrough in 2000, say, which deals with a special case when Q is the power of 2. And but mathematically it's quite complicated, but at least in characteristic 2 it can be done quite efficiently, and the other things actually work also fairly well, say. I don't want to say anything about this. So there's another thing which is a bit more special construction, say, so-called subfield elliptic curves, or say Kopitz elliptic curves. Well, it's kind of reducing to the first case, but to an easier instance of the first case. So what you do is you choose your A and B not in FQ, but in FP. So Q is the power of P. FP would be a very small field, so P could, for example, be 2, then there's not much choice, and Q could be still a large power of this P. Okay, and then it's actually quite easy. Well, if P is small and it's not very complicated to compute the number of points, maybe by just enumerating them. And if you know this, then there's easy formula, say, to derive from this number the number of points on the elliptic curve defined over FQ. Okay, so this is a very efficient way to go, but you can't really get many elliptic curves from this. So once you have the number of points, what you would check is, well, you divide out small prime factors of your number, and then you hope that the thing which remains is prime, and you do some random primality test in order to ensure with sufficient probability that the remaining thing is actually prime, so that this would be your L. Okay. So, and then there's another method which is also liked by mathematicians, say, more than maybe practitioners, which is called complex multiplication elliptic curves. This is also a very strange, well, this is a kind of interesting method. So in some sense, you're doing other stuff, and in the end, what pops out is an elliptic curve, and you a priori know what the number of points would be. It's kind of a magic construction, say. But also you get quite special elliptic curves. You can't get them all. Okay, so philosophical remark here. This subfield and complex multiplication construction, yeah, they actually yield curves which have more mathematical structure than the first construction, like just taking in random curves. Yeah? And the point is, what sometimes is argued is that this additional structure might actually be of use, of potential use, say for attacks like weakening the ECDLP, for example. Yeah? And well, so far nothing has been found, or nothing really serious, say. But it's more like a philosophical remark. I mean, basically in cryptography, what cryptography is actually basically about is you have something which is structured and you would like to transform it so that it actually looks unstructured. Yeah? You want to impose chaos and you would like to destruct or remove structure from things. Yeah? That's what everything should look like random noise in some sense. Yeah? But then, using some magic thing or some secret information, actually from this random noise, you would like to again construct the specific, the structured information which actually was behind. Yeah? And well, in some sense, using subfield E in complex multiplication E would actually contradict this philosophy a little bit, because you actually impose more structure in order to get the objects with which you would like to work. It's actually better to not impose so much structure, and so some people argue that random elliptic curves are the way to go and you shouldn't use subfield curves or complex multiplication curves. Yeah? But that's probably a matter of taste and trust, I guess. Okay, so insecure cases. So there will be 5 cases now, and it's going to be a bit more complicated, I guess, but it's, we are also, after this we are going to be finished. Insecure cases. So there's a couple of insecure cases where one has to take some care. Okay, one is called multiplicative transfer, or say Freirückreduction, or Meneses-Okamoto-Venstone attack. This dates back about the beginning of the 90s, I think. So what happens there? Well, assume that the prime L divides q to the power of k minus 1 with, say, some small k, or not too big k, hopefully. What turns out to be possible is the following. You can take the ECDLP and you can actually compute by a kind of an arithmetically easy computation. You can turn it into DLP in the finite field of q to the power of k elements. Yeah? So, and now, of course, well, if in the finite field that discrete logarithm is kind of more easily solved, then you can solve it there, and then you can recover the original solution on your ECDLP, of course. Huh? So this, you transfer the difficult problem into kind of into an easier problem, say. Okay. Okay, it's not that easy in fq to the power of k. It's still a quite hard problem, say, but it's considerably easier. Can be considerably easier than on the elliptic curve. More information on this is the following. If I take random and independent Q and L, yeah, well, if I assume those values are kind of independent, what one normally has is that L is of, that the K, which we have to consider, is of roughly equal size as L, yeah? Which means L is huge, so K is huge, and then the DLP in the finite field is not more easily solved because the finite field is absolutely huge, yeah? So then it's of no use. But, and this was kind of a surprise, if you take a special class of elliptic curves, so-called super single elliptic curves, well, they're defined by that the funny number t, which we had before, is congruent to 0 mod p. In those cases, yeah, the k is always small, surprisingly, yeah, no matter what q and l are in some sense. They are kind of, q and l are necessarily related such that k would be small. And in those cases, the ECDLP actually, well, the DLP in the finite field is much easier than the ECDLP in the original setting. Yeah? Which back in 91 led, people said, oh no, you shouldn't use super single elliptic curves in cryptography, and they were actually banned from cryptography whatsoever. Interestingly, like in the beginning of the 2000, around 2000 or 99 or something, they entered the scene again because you can do still, the DLP is much easier, but it's still quite hard, and it's still actually, you can do something very useful with those ones. Namely, I just want to mention the thing, it was kind of a hype in the last couple of years, it's called identity-based cryptography, where you actually can replace traditional public key infrastructures by kind of a different setting, say. Okay, so this is one attack. Here's another one. This is really devastating, but it's also very special. It's called additive transfer, also by or it's called smart ass attack. Yeah? So smart, this guy in England, Iraqi, Semav, and the Japanese guy, I can't remember the name at the moment. So this dates back to 97. And yeah, here one assumes that L is equal to P, so this is a very special case. Yeah? But these things actually have been used in practice, I think by Motorola, for example. And okay, so one thing, well, what turns out to be possible is to transfer the ECDLP into a DLP in FP plus. So this, I haven't really defined this. This is like the group of where you take addition instead of multiplication in FP. And the DLP in this FP plus is extremely easy. You know, so it doesn't take any time for the computer to compute it. It really can read it off kind of instantaneously. Which means that in this case, L equals to P is absolutely totally insecure and you can't really use it for cryptographic purposes. Okay. So here's another one, more recent. So these ones are called veil descent. Well, it's called veil descent methodology or covering attacks. And well, I've been involved in this as well. This is like from 2000 up to 2003 and applies, well, mainly applies to curves over in characteristic 2. So where Q is a power of 2 and P is equal to 2, say. Huh? So what one has here is one has a small finite field, FQ. One has a big finite field, a capital K, that would be FQ to the power of N, and an elliptic curve over the big field. So that's the working setting. And what happens to be the case is the following. By kind of a, say, miraculous construction, if you wish, you can come up with something which is a more general object like E, so it's called an algebraic curve C0, and where the coefficients are not over the big K, but over the small k. So this thing can be constructed. Furthermore, you can transfer the ECDLP in the elliptic curve over the big K efficiently into a DLP in some other funny object, which is called peak 0 of C0, say, yeah? So this peak 0 thing is kind of a generalization of the point group of the elliptic curve. I don't want to explain how it actually works in practice. It's also a group. Yeah? It can also be implemented, say, as a black box if you wish. So, and this ECDLT can be transformed into this peak thing, and then there are certain cases in which you can actually solve it more easily in the peak thing again. Yeah? Okay, and this leads to a security reduction. Well, in certain cases, if n is greater or equal to 3, but still small or medium size, say up to 31 or something. It's not as, say, devastating as the two previous attacks, but it has to be taken into consideration if you would like to use your security margin or something. Yeah? So, and this is the latest thing in the story so far. So this is so there's always an annual conference which is held in Canada and in Essen in Germany here about elliptic curve cryptography. And this is, it's always held in September, and this is kind of information which was presented there on the one this year. So it's the latest attack. It's called, say, index calculus attack via summation, polynomials, and veil restriction. The following three guys have been involved in this. And okay, so what this does is it doesn't really transfer the elliptic curve cryptography problem into a different group where it might be more easily solved, but it actually uses the structure of the elliptic curves, which is, this is kind of a novum, say. Yeah? So far the assumption was, as I pointed out, that in the general case, you shouldn't be able to use the structure in order to gain a speed up over generic methods. Yeah? But this attack actually uses the special structure in order to achieve a speed up. So this is kind of, it's quite interesting actually. Okay, so what are they doing? So they, on those points, on the elliptic curve, yeah, they introduce kind of a size notion. So if you can have small integers, you can have big integers, say, so you can have small points or you can have big points in some sense. Yeah? And also the following should hold, that points, or say smallish points, actually decompose into a small number of small points, whatever that's going to mean. Yeah? So if you have an integer which is not too big, then the likelihood that it decomposes into small prime numbers is also quite high. Yeah? So this is kind of it's kind of an analogon of prime factorization. And then using standard ideas from index calculus, which one actually also uses for the attacks in finite fields, which make them weaker than elliptic curves so far. But you can use kind of similar ideas and actually gain kind of a speed up in certain situations. So the general statement is the following. So the ECDLP in the elliptic curve over f cubed to the power of n can actually be computed in this time. So that's roughly, say, q to the power of 2. Yeah? for fixed n and q growing q. So it's an asymptotic result. Okay, so if you compare this with what was expected before. So before we thought, well, L is roughly of the size of q to the n in this particular case. Yeah, and before one thought actually, oh, the time should be roughly, say, L to the power of 1/2, which in this particular case would then be q to the power of n over 2. So this was the assumption that this would be the time it would take to solve it. Yeah? But as it turns out, asymptotic at least, if q is large enough in comparison to n, the time is just q to the power of 2. Yeah? So if n is some number, say 10, then that's the difference of q to the power of 5 to q to the power of 2, which makes a considerable difference. Yeah? And this works for all elliptic curves in this particular case. Yeah? But it's an asymptotic result, and well, practical implications have yet to be investigated, actually. And even more interesting, if you impose kind of a certain condition on n and q, both together, so if you say n should be of roughly equal size to log q, and they should both actually tend to infinity, well, if you make them large enough, then it's actually possible to compute it much more efficiently than q to the power of 2. Which caused some stir up actually at the ECC in 2004, because people didn't expect this to happen and were quite kind of say kind of excited about it, say. Okay, the morale of the story is that the ECDLP for small or medium n and general q may actually be weaker than one would actually expect from the general philosophy I mentioned a while ago. Yeah? So this may is, well, it's not really, well, one actually would have to do some implementation and see actually whether that really fast, and there's also some heuristics involved in the whole thing, but there seems to be some indication. If you are very prudent and would like to avoid trouble whatsoever, then it might be prudent actually to avoid small or medium n in comparison to q. These things actually would be used in practice, yeah? So it's, you might regard them as a bit suspicious, if you wish. Okay. So, okay, now this sounds all quite complicated, and one might get the impression, this is all complicated, and elliptic curves are kind of a minefield, say, and you wouldn't like, we really don't want to use them. But in fact, it's all these, well, if you investigate the methods, they all apply to only very special cases. It's a very small subset of elliptic curves. Yeah? So in some sense, it's very easy to avoid them. Also, the last two attacks I mentioned are not really like, well, if you can do it, then your system would be insecure. That's not the case. It might just be 1,000 times weaker or so than you actually anticipated. But if computed to the current one, with current technology, would compute, I don't know, 1 million years or something, or maybe much more, like 10 to the 20 years or something. If you divide by 10 to the 3, it doesn't make so much difference, say, in principle. Yeah? So these attacks are more like, say, scratching on the surface, but are not really devastating for elliptic curves, say. Okay, well, how would you avoid them? So they can be easily avoided, for example, by the following means. Well, you could use random elliptic curves to avoid structure whatsoever. Yeah? That's one thing. Not use any particular structure which might be exploited in attacks. Could be one philosophy. And, well, in addition to that, you could also only use, say, prime fields. Those might actually be the most secure, say. Or you use extension fields where p is small and r is a big prime. Shouldn't be a composite number. Yeah? So these choices would be actually quite prudent, say. Because if you look at the previous attacks, especially the last one, it wouldn't apply in those cases. Yeah? Okay, and here's another thing. If you use a standard, or if you want to communicate with somebody, yeah, then he might actually say, please use this curve. Yeah? So, for example, in these standards, sometimes people might be affiliated to US investigation authorities or something. That actually does happen. And they propose some curves to use, yeah? Because they say, we have investigated, this is really secure. Huh? But then the question, of course, is how much do you trust them? Yeah? Well, here's a little trick which actually is, I find is quite handy. So this is, if you have to accept somebody else's curve, you can at least kind of, check that or you can require that it was created verifiably at random. Yeah? So what does that mean? what you would like to have is that the guy who provides the curve to you has actually chosen A and B at random and hasn't constructed them so that the curve has kind of hidden weaknesses or something. Yeah? And in order to achieve this, you require that actually A and B should be given via, say, cryptographic hash values of 2 published numbers. So you require your other party to present 2 numbers, and then you apply, say, SHA-1 or something to it. And then those numbers which you get from this should be your A and B. And then the assumption is, if he has actually chosen A and B first, then he actually would have had to re-engineer the pre-images of the cryptographic hash function, which is an assumption, well, one assumes that this should not be possible. Yeah? So, well, in turn, you assume that he has first actually chosen the numbers, then computed A and B, and then just taken this curve without any further thing. Yeah? Also, one assumes that these outputs of hash functions are really kind of like random values in comparison to the input, so that A and B actually would appear to be randomly chosen. Yeah? Okay. So, conclusion. Okay, so this is the first thing, say, well, basic statement. Elliptic curves can be used to implement group-based cryptography. Yeah? Cryptography can also be based on other assumptions, say RSA or so, but if you stick within the group-based setting, then elliptic curves actually appear to be very useful. They also provide a high efficiency and security ratio. That's what I've said. And well, what we've also seen, research in possible attacks is still actively carried out, another thing. So in some sense, there might be further surprises, but I wouldn't expect really kind of a general breakthrough for general elliptic curves. That seems kind of unlikely to me, but that's always speculation, say. Also, the known attacks can all quite easily be avoided using random elliptic curves and suitable finite fields. Yeah? Don't use any finite fields which have a kind of a composite extension degree, say, or, well, if you're really kind of paranoid or so, really try to use your own random curves and don't take any curves for granted or so, or check the verify and be created at random property if you wish. So, kind of as a last remark, I really haven't talked about this. Also, kind of a big business at the moment is quantum computing, say. Well, this was kind of a breakthrough in '97 actually, and so that was Peter Shaw, and also here in Berlin actually got kind of a prize for this Nevanlinna prize at the ICM in '98 in Berlin. So where he showed that so quantum computers are kind of different from normal computers because they can do certain operations in parallel. Yeah. So where, say, on a classical computer you would need exponential time, a quantum computer can do certain things in polynomial time. Yeah? And so this Peter Shaw actually showed that, in theory at least, a quantum computer could be used to completely break, say, elliptic group-based cryptography, in particular elliptic curves, but also RSA. Yeah? And so this is something which one has to keep in mind. I mean, at the current state, nobody thinks that quantum computers can be built in the very, say, near future, or if they can build at all. But it is kind of a threat to the whole thing, and maybe, I don't know whether we live long enough to see the advent of quantum computers, but I think there are estimations like in 70 years or so, they might be able to build some decent thing or so.